Hello everyone, welcome to this tutorial on characteristics of sound waves. In this tutorial, we will learn to demonstrate how to generate a sound wave, frequency response of a sound source, how to calculate velocity of sound, interference and beats of sound waves, forced oscillations of a sound source, and show XM grace plots, Fourier transforms, and circuit diagrams for our experiments. Here I am using XSpice version 3.1.0, Ubuntu Linux OS version 14.10. To follow this tutorial, you should be familiar with XSpice Junior interface. If not, for relevant tutorials, please visit our website. Let's first begin with definition of sound. Sound is a vibration that propagates as an audible mechanical wave of pressure and displacement. It requires a medium to propagate. Medium can be air, water, or any metal surface. In this tutorial, we will carry out various experiments to show characteristics of sound waves. Let's perform an experiment to show frequency of sound waves. In this experiment, ground is connected to piezo buzzer. Piezo buzzer is connected to SQR1. Microphone is connected to A1. Here, piezo buzzer is a source of sound. This is the circuit diagram. Let's see the result on the plot window. On the plot window, under Setting Square Waves, set the frequency as 3500 Hz. Click on SQR1 checkbox. Frequency of SQR1 is set to 3500 Hz. A digitized sound wave is generated. Move the frequency slider to change the waveform. Click on SQ1 and drag to CH2. Input data of SQ1 is assigned to CH2. A square wave is generated. Drag the millisecond per division slider to set in compressions and rear fractions. Click on CH2 and drag to Fit. Voltage and frequency of SQ1 is displayed on the right side. Move the frequency slider to set in sound waves. Sound wave produced by the piezo buzzer is shown in black color. Amplitude of the wave changes as piezo buzzer is moved closer and away from the mic respectively. Now we will demonstrate frequency response of piezo buzzer. On the plot window, click on Experiments button. Select Experiment List opens. Click on Frequency Response from the list. Two new windows, Audio Frequency Response Curve and Schematic open. Schematic window shows circuit diagram of the experiment. On the Audio Frequency Response Curve window, click on Start button. Frequency response of the piezo buzzer is set in. Frequency response has maximum amplitude at 3700 Hz. On the same window, click on Grace button. Grace window opens showing frequency response curve. Now we will measure velocity of the source of sound. On the plot window, click on Experiments button. Select Experiment List opens. Click on Velocity of Sound from the list. Two new windows, Eyes Junior, Velocity of Sound and Schematic open. Schematic window shows the circuit diagram of the experiment. On Eyes Junior Velocity of Sound window, click on Measure phase button. We can obtain different phase values by changing the distance between mic and piezo buzzer. Click Measure Phase button to obtain different phase values. From the various phase values, we will use 178 degrees and 106 degrees to calculate velocity of sound. We can obtain these values when piezo is kept close and 2 cm away from the mic. To obtain accurate results, ensure that mic and piezo buzzer are placed on the same axis. To calculate the value of velocity of sound, we have the formula as shown. Velocity of sound obtained from the experiment is 350 meter per second. As an assignment, calculate the value of wavelength of sound. Formula: lambda is equal to V upon F. Now we will demonstrate interference, beats, XM grace plot, and Fourier transform of the two sources of sound. To show grace plots in the experiments, make sure that you have installed Python Imaging TK, Grace, SciPy, and Python pygrace on your system. In this experiment, we use two piezo buzzer as source of sound. In this experiment, piezo 1 is connected to SQR1 and ground. Piezo 2 is connected to SQR2 and ground. This is the circuit diagram. Let's see the result on the plot window. On the plot window, set frequency as 3500 Hz. Click on SQR1 and SQR2 checkboxes. Frequency of SQR1 and SQR2 is set to 3500 Hz. A digitized sound wave is generated. Move the frequency slider to change the waveform. Click on Experiments button and select Interference of Sound. Eyes Interference of Sound window opens. At the bottom of the window, change NS, that is number of samples value, to 1000. Click on SQR1 and SQR2 checkboxes. Click on Start button. Interference pattern is seen. Now click on XM grace button. A new window opens with a grace pattern. Now we will show beats pattern. Click on Experiments button and select Interference of Sound. Eyes Interference of Sound window opens. At the bottom of the window, click on SQR1 and SQR2 checkboxes. Click on Start button. Beats pattern appears. Now click on XM grace button. A new window opens with a grace pattern. Click on FFT. A new window opens with Fourier Transform. To know more about Fourier Transform, please visit this web page. Let us perform an experiment to show a low frequency sound wave. This is the circuit diagram. Click on Experiments button and select Interference of Sound. Eyes Interference of Sound window opens. At the bottom of the window, set the value of SQR1 to 100 and check the box. Click on Start button. A low amplitude wave is displayed. Click on FFT to obtain a grace plot of Fourier Transform. Let's summarize. In this tutorial, we have learned to demonstrate how to generate a sound wave, frequency response of a sound source, how to calculate velocity of sound waves, interference and beat pattern of sound waves, forced oscillations of sound source, and have shown XM grace plots, Fourier transforms, and circuit diagrams for our experiments. As an assignment, capture a sound burst. Hint: a bell or a clap can be used as source of sound. This is the circuit diagram. This video summarizes the spoken tutorial project. If you do not have good bandwidth, you can download and watch it. We conduct workshops using spoken tutorials and give certificates. Please contact us. The Spoken Tutorial project is funded by NMEICT, MHRD, Government of India. This tutorial is contributed by Kaushik Datta and Madhuri Ganpati. This is Sakina Sidhwa. Thank you for joining.